Okay. And I'm unmuted, I think.
Yep, yeah, I think we're all set. Cool, okay, so welcome back from break, everybody. For our first talk of the semester, we have Galanis visiting from PI. He did his PhD at Stanford under Sophthermopoulos, and now he's working at Perimeter. Today he's going to tell us about some new astrometry ideas that he's been working on recently.
All right, thanks, Arik, and thanks for the invitation and everyone for being here. Yeah, I should preface this by saying that I'm trained as a particle physicist at Stanford. I'm not an astronomer or an astrophysicist. But some ideas coming from photodetectors in dark matter experiments made us, with collaborators, think about intensity interferometry. And then we ended up doing some purely astrophysics work on astrometry, and then some recent work on AGN physics that I'm going to talk to you about. I tried to cater a bit to particle physicists' interests, so I'll focus more on some applications that might be of interest to you, but there are also many pure astrophysics applications, so if anyone is interested in the end, they can ask. Okay, so I'll assume you don't know what intensity interferometry is, and I'll explain it. So to start, I'm going to tell you very few things about telescopes, imaging telescopes, and phase interferometers or Michelson interferometers, how they work, their principle, and then I'll go into intensity interferometry, the basic principle of the technique that was proposed in the 1950s, and go through the traditional application, which is measuring the size of stars on the sky. Then I'll tell you how new technologies can allow us to, instead of targeting stellar diameters or stellar morphologies, target morphologies of AGNs, active galactic nuclei, and their accretion disks in particular, and establishing a geometric method to measure the Hubble constant, which is ongoing work, hopefully will be published next month, mainly with Neil Dalal at Perimeter. And some other collaborators who are more experts on the AGN side. And finally, hopefully I'll have time to go over a new technique or a modification of the traditional technique that we proposed with collaborators, all of them particle physicists, in July, which will allow to go beyond morphologies and take advantage of new technologies to do astrometry, so measure very well the distance of two stars on the sky. And I'll explain how this works and go through some scientific applications, most of which are, well, all of them are astrophysics, but probably I can tease some BSM physics at the very end. All right, so to start with,
The first two parts are the traditional technology, but the third part is new work done with Marshall.
Yeah.
The new work came out earlier than this traditional.
Yeah, exactly. So first we thought about, because, well, this idea came from Ken and Masha. They were first thinking about astrometry. You know, they have done this halometry from astrometry thing where you take Gaia data and then you try to see objects that pass through a sea of stars and see correlated motion of stars. So this is where astrometry came from. And to do astrometry with this technique, you need the new thing. But then with Neil, we realized that actually you can just do AGN physics with the technique as it exists, and just nobody had proposed this before. It's a pretty obvious application, and I can tell you why no one has thought about it. But yeah, it's true. All right, so to start with telescopes, you're probably all familiar with them. So here I'm just showing you a picture of the Keck Observatory in Hawaii, in Mauna Kea, one of the most advanced telescopes that we have. These are very complicated instruments. Not only it's very hard to build them, Polish mirrors to sub-wavelength precision. The Keck has 10 mirror, a 10 mirror aperture. There are whole groups of people working on modern telescopes to make them work and do the data analysis afterwards. However, even though these are very complicated instruments, there's one fundamental quantity, which is the diffraction limit of a telescope, which is telling you how well you can resolve two sources. And this is fundamental in the sense that it comes from the wave nature of light. And it's the diameter, the wavelength at which you're observing over the diameter of your telescope, roughly. So this is on the order of milliarcseconds. If this unit doesn't tell you much, it will in a bit. But in any case, ground-based telescopes have a particular issue, which is the atmosphere. So you can think of the atmosphere as a very bad piece of glass that you put in front of your telescope, and this glass actually fluctuates. So what you see when you look through the aperture of such a telescope is your star, which should be one spot on the sky, moving around in your in your photodetector array, in your CCD camera. The reason is you have the atmosphere, you have patches with different index of refraction, so you get all sorts of aberrations. And seeing what it does is, as you can see, not only does it make the image move, but it sort of widens the spot as well. And this is what you're seeing here is very slowed down. This fluctuation happens on millisecond timescales, and this is the fluctuating timescale of the atmosphere. So actually what you see over long exposures in your telescope is some averaged position of the star. And this is called the seeing disk. So this average position here, this circle I'm showing you here, is basically the seeing disk, what is called the seeing disk. And equivalently, this reduces the resolution of your telescope. If you have two sources within this seeing disk, you won't be able to see them. So instead of having lambda over d, over the diameter of your telescope, you have lambda over R0. This is called the Frick parameter. And it's roughly 30 centimeters. It's set by the atmosphere. And this is telling you that instead you have a 10-meter mirror, but actually your resolution is like if you had the 30-centimeter mirror, which is pretty, an order of magnitude and more suppression in your resolution. And what the larger mirror buys you is more photons. Yeah.
Does it depend on the temperature or pressure or other properties?
Yeah, it depends on the, well, it's the index of refraction of the atmosphere, which depends on the density of air, etc. Yeah, and it gets contribution from the line of the column of air through which you're looking at. Yeah.
Thanks.
Exactly. So to go beyond the seeing disk and recover the diffraction limit of your telescope, you need adaptive optics, which is what these lasers that you see here do. What they do is they create an artificial star on the sky. And by tracking how the star, the position of the star changes, which you know perfectly because you are producing the star, you have some deformable mirror that takes the reflected light into account, corrects the wavefront, and then you use this correction to correct the wavefront from the actual stars. And it's a very complicated technology that also loses a ton of photons in the process. And actually they got a Nobel Prize for this, Andrea Ghese's group in UCLA and other people, but I forget. Right. However, the telescopes that don't suffer from this are space telescopes. So for example, JWST, there is no atmosphere in space, so you regain the diffraction limit of your telescope. However, the issue with space telescopes are that first, it's very expensive to shoot them in space. JWST costed what, $14 billion, whereas the two Keck telescopes, I think, cost like $90 million each, I think, adjusted for inflation. So this is much more expensive. The technology becomes obsolete the time you shoot it in space, whereas ground space telescopes you can continuously improve. And then because these need to be deployable in space, they're usually much smaller in diameter. So you can't really shoot a 10-meter mirror in space, although JWST is actually pretty big. It's 6 meters, I think. Right. So this is why it's still useful to have ground-based telescopes, especially with adaptive optics nowadays. Now, instead of just taking pictures of the sky, which is what JWST or Keck does, we can also do astrometry on the sky, and there are some dedicated instruments like Gaia here, that are trying to measure the positions of stars very, very well. So even though Gaia is a much smaller, has much smaller apertures, I think the mirrors are, it's like a square mirror of 1.5 meters by 1. So it's pretty small compared to this telescope or Keck. And the resolution is pretty bad. It's 400 milliarcseconds compared to 30. However, what it buys you is light-centroiding, and I'll explain what this is in the next slide. But essentially, the idea is that resolution is how well you can see two things that are close together. What is the minimum distance they can be to see them? And light-centroiding is how well you can pinpoint the center of this light curve. So this is light-centroiding comes, improves as you get more and more photons. And Gaia plans, to have a catalog of billions of stars, measure very precisely, and for the best measured stars at the end of mission, the light-centroiding precision is going to be something like 30 microarcseconds. If this doesn't tell you much, just remember the number of 30 microarcseconds to compare it to what our technique will be able to do later. Spoiler alert is sub-microarcsecond. So,
yeah. What's this quantity? Sigma, delta, theta?
Yeah, this is light-centroiding, and I'm going to explain a bit more what this is. So, right, resolution of a telescope versus light-centroiding. Here, what I'm plotting is what you would see in your photodetector if you had two stars, 2 point-like objects that are close together. If they are too close that they are unresolved, this is the usual Airy patterns, like this sine x over x. So unresolved means that you cannot see that there are two bumps here, the two point-like objects. And this is because of the diffraction limit. So this is resolution. And SNR is telling you, or light-centroiding is how well you can measure each of these points, how small the error bar is. And the more photons you measure, the better you can pinpoint this curve. Okay. In principle, if your optics are perfect, this is just shot noise. In reality, it's how well you can know the PSF of how well you can know the imperfections of your optics, and the imperfections of your optics, essentially. For space telescopes, for ground-based telescopes, it's also the atmosphere and how well you can know the adaptive optics and things like that. So this is what I mean by light-centroiding. I mean that even if I have two stars, Gaia might not be able to resolve stars below half an arcsecond, but it can pinpoint the center of the two stars to very, very well. And this is what I mean by this sigma delta theta, which is resolution over SNR. Whereas resolved sources are this. When I take these stars farther apart, resolution is being able to see these two bumps. And resolution with high SNR is, again, the same with smaller error bars. So that's the difference between the two.
What is light-centroiding useful for? Like, why do I care about knowing the centroid of two stars?
Well, you care, depends on the application that you're interested at. So, for example, if you have if you have a binary that is tight, you can know very well where the binary is, and if something affects the binary as a whole, then you don't care about the position of the two stars by themselves, but you care about the centroid of the stars, right?
But I can't tell that it's a binary as opposed to one really bright.
Exactly. Yeah. Like if you're trying to do, I don't know, like the first example that comes to mind is this thing Ken has worked on, and Neil Weiner, on having, looking at the Gaia catalog and seeing if some object goes through the stars and produce some correlated motion in many stars. If you have, I don't know, something like a black hole or a dense dark matter clump, what you care about is how the centroids will move, and not specifically each one of the two stars in a binary.
Okay.
Right. Yeah. Because it will affect as a whole since they are close together. Right. And Gaia is in this limit if the stars are below an arcsecond. Okay, so Michelson interferometry or amplitude interferometry or traditional interferometry. I'll spend one slide on this. It's actually a double slit experiment, so it's not much complicated. Your slits are your two telescopes. Slit one of diameter d, the diameter of your telescope, And then the distance of the two slits is the baseline between the two telescopes. So as you know from a double slit experiment, if I take light from the two slits, I shoot light, I shine light on my screen. Light gets there is interference between the light that goes from the one slit and the other slit, and you see an interference pattern on your screen far away. This is the same principle here. You get light from some object on the sky. You recombine the light physically in some photodetector, and then you look at the interference pattern of this light front to tease out properties of the source that you're looking at. So here I'm plotting the first star that was measured with Michelson interferometry was Betelgeuse, which is the largest star on the sky. Actually, now I think it's the second largest, something like that. But it's one of the biggest objects on the sky that you can resolve, other than the sun or the moon. And its angular size is roughly 45 milliarcseconds. What you see here is what you would see in 1D is some intensity in arbitrary units in your photodetector array. And I'll play this movie as I make the baseline larger. So from 40 centimeters to something like a few meters, you see how this thing changes, and I'll explain it a bit more. So you see interference pattern, an interference pattern fringes. So as I'm making the baseline larger and larger, or I take the slits farther and farther away, you see this interference fringes here. And with orange, blue is Betelgeuse, and orange is Sirius, which is 10 times smaller. And you see two scales. There is this scale, this overall scale, this envelope here, which has a characteristic size of lambda over d, large d, the diameter of your telescope, similar to a double slit experiment. And then there's the smaller scale, which is lambda over the baseline. So here you are able to see features that occur over 1 over lambda over b instead of lambda over d. Okay. And the important thing in interferometry is that you see some interference fringe, which happens when you have something like a point source, right? If I have a plane wave and it goes through two slits, I see the full interference pattern in my screen. But if I have many sources and there are many path lengths interfering with each other, the interference pattern is washed out at my screen. And this is what you see here. As you start resolving a source, so think of a star, and from it being a point object, it becomes larger and larger. So you have many points that have vastly different path lengths coming to your telescope. And all this in the end will interfere destructively as you start resolving the star. And this is what you see here. So the interference, the Imax, the maximum intensity minus the minimum intensity, this quantity here diminishes more and more. And at some point, it vanishes completely. And this is when you know that you resolved your star. In contrast, so here I chose what Michelson and Pease did in the 1920s. They had one photodetector and two mirrors, and they took the mirrors farther and farther apart, and they looked at the interference pattern with their eyes. And what they saw, or what they would have seen if there wasn't for the atmosphere, would be interference fringes from the star. And as you take the mirrors farther and further away, or as you make your baseline larger, at some point you lose the interference, and you know that you resolved the star. So interferometry is basically seeing some interference, and then losing the interference. And when you lose it, you know that you resolved the star. In contrast, Sirius is not resolvable by this baseline. You would need something roughly 10 times larger to resolve this star. So you still see the interference fringes if you looked at Sirius. Now, the observable of amplitude interferometry, of Michelson interferometry, is basically electric field in telescope 1 and electric field in telescope 2. And this can be quantified by this correlation function, the electric field in telescope 1, when you combine it with electric field in telescope 2. And there is a very famous theorem, the fundamental theorem of optics, interferometry, the Van Citter-Zernike theorem, which tells you that this correlation function, is the Fourier transform of the intensity distribution on the sky. So this is an actual image of Betelgeuse that we have today. I took it from here. And this correlation function is quite literally the Fourier transform of this quantity, of this 2D quantity on the sky. Okay. And this is called the visibility for those of you who are familiar with the word. Right. So essentially to sort of find the diameter of the star or to find features of the star, you take your observable, which is this, and you Fourier transform. There are interferometers nowadays that do exactly this job. We have optical interferometers. Again, the resolution of an interferometer is lambda, the wavelength that you're observing at, over your baseline, similarly to lambda over aperture of a telescope if you have a single telescope. So we have something like the CHAR array, whose baselines can be are on the order of 200, 300 meters, and operate in the optical. And what they do is basically you have these telescopes here. You see light. You collect light from these telescopes here and here, and then you recombine it with some central facility physically. So you have these arms here, path lengths that recombine the light there. However, if you are trying to do this in the optical, there is an issue, which is first you need to know this baseline to sub a wavelength precision. You need to know your path length very well. So this means that you need to know this baseline to below a micron or half a micron, and this becomes very expensive, prohibitively expensive as you make your baseline longer. And of course, you cannot really do this if you wanted baselines on opposite sides of the Earth, let's say, to get the best resolution that you could hope to get. For this? Yeah. Yeah, exactly. So if you're trying to do this, you need also adaptive optics. And not only adaptive optics, because as I said, adaptive optics sort of measures the wavefront distortion and corrects the wavefront distortion. But this is a statement about the derivative of the wavefront. So there's also a mismatch of the absolute phase. So on top of adaptive optics, these modern interferometers also do fringe tracking. So basically trying. Yeah, you need to correct for the atmosphere.
If you're working in radio or atmosphere, then that's pretty negligible.
Yeah, in radio, atmosphere doesn't matter. And on top of that, radio is also better because you can do baselines as long as the Earth. The reason being that instead of physically interfering the light in hardware, you can record every oscillation of the electric field and then interfere light in software. So what they do is they have this, if you've seen the pictures, they put all the data in many hard drives, and then they ship all the hard drives to some central facility to process them. And that's what they do. They measure every oscillation of the electric field. Right. However, this you cannot do in the optical because there are no photodetectors that can do this.
So they also have to know the distance between their observatories really well.
Yeah. Exactly. So they need to do millimeter, which is what they observe at. But this can be done, in radio. And I think it's a few millimeters to a bit more, and then because that's also something that we thought about. It affects us too with our technique. You can go down to a millimeter. The next iteration of this global VLTI observing system is going to do like a millimeter. Yeah, they have demonstrated 1.6. Right. So and by doing this, they managed to look at something that has a get angular resolution of roughly 30 microarcseconds, and managed to get this image of the black hole of M87 and of our galaxy. So if you wanted to have the best resolution possible from something from the Earth, what you would ideally need to do is keep the baseline, the wavelength as short as you can, so optical, and have a baseline as big as you can, which is Earth size. Okay, but optical interferometry cannot do this, and this is where intensity interferometry comes in. So I'm going to explain the basic principle of intensity interferometry before talking about the actual application of stars. So okay, this will be a bit technical. So if you have any questions, just ask them. Well, not technical, maybe a bit more complicated. So here I'm showing you the intensity of light from a natural source, let's say a star or a lamp, not a laser, and that's crucial, from a natural source as a function of time. And time here I'm measuring in femtoseconds. Here you can see oscillations or fluctuations of this intensity over femtosecond time scales, right? And this I'm going to call macroscopic fluctuations. Whereas this dashed line here is the average of this line intensity over some long time, let's say a microsecond, let's say, or a second, whatever. Yeah, yeah, this is what I'm going to say. So what you're seeing here, this is a property of chaotic light itself. This is super Poissonian statistics, if you know the word. If not, this is a property of the fact that that you have many frequencies, coming from the same source. So this is basically bitting. If you have, two tuning forks slightly detuned, you get bits at random places with random amplitudes. And this is what you see here, a random amplitude when you have many wavelengths interfering with each other, which is why I'm saying it's a chaotic source and not a laser, which is strictly monochromatic.
But it's also because the source is very far and very faint, right? It very near.
Well, I can have a hydrogen lamp over there and I would see the same. In fact, the first demonstration of this technique was with hydrogen lamps in the lab.
There seems to be some characteristic scale in this part.
The size. Yeah, the size is set by the right. So this is basically the intensity. If you did the electric field, you would see this field just like in bitting in two tuning forks, and the oscillation period would be set by the wavelength, but these bits would be set by the delta omega, the delta lambda, the spread in wavelengths that contribute to making this. This is what sets the characteristic frequency.
So
Yeah.
the spread of the source is
yeah.
Photon frequency.
Yeah, exactly. And femtosecond comes about because 2 pi over lambda for optical light is a femtosecond for like 500 nanometers. Right. So, and I want to stress that this is not fluctuations that come from the atmosphere or coming from, having a star and having a spot that moves around the star or whatever else. This is a property of chaotic light itself. Okay. And the property is the following thing, is that when you calculate fluctuations, when you calculate fluctuations of this thing on very short time scales, you see these macroscopic fluctuations there that do not go away in the limit of infinite photons. So if you have a laser, you usually talk about shot noise. And then if you measure the mean intensity of your laser again and again and again, you have a long exposure, you can pin down the average intensity better and better for a perfect laser. However, here, if you're doing femtosecond timescales, what you're pinning down is this whole curve. You're not pinning down the average. Okay. In other words, when you're looking at a star, you never talk about these fluctuations. You say, the sun has a flux of that, or a random star has a magnitude of, 8. It never fluctuates. And the reason is this is a time average thing over time scales that are much longer than a femtosecond, clearly. Okay. These appear only if you do femtosecond. If you resolve timescales on the order of femtosecond. And to see this a bit more, if you put a photodetector, this telescope here is a photodetector, the fluctuations that you will see in the mean number of photons are going to be shot noise. So N0, the square of this is going to be Poisson. But you're going to see some super Poissonian statistics that go like N squared, and N squared is exactly this macroscopic intensity fluctuation itself. So it's the fact that you have, more here compared to less here, or fewer photons here. Okay.
So again, can you explain a bit more detail? How did you generate this curve? Did you source by two frequencies with a fixed separation?
A spread. Let's say, so here the only thing I put there is that the spread is smaller than the wavelength. So let's say the wavelength is 500, the spread is 500 nanometers over, something.
So you have a source of two typical frequencies with some spread. Just
one frequency with a spread. Yeah. Think of a collection of gas with, with collisions, and you get some Doppler broadening of the line, and this is basically what this is.
Photon emitted is a random frequency sampling of the spread.
Exactly,
Also,
yeah.
what's about phase? Are there phase follow some rules or are just random?
Right, so I'm talking about intensity, so I'm only talking about photons. I'm just sampling photons from this curve, from this spectrum. There's no electric field coming in this picture. Okay, it's just the fact that you would measure more photons. Right, so if you have a photodetector there, you would measure more photons here. So this wave is passing through, right? You have a photodetector and this passes through.
Source and phase, that matters.
Oh, phase in terms of where you are at in the wavefront. Yeah, it's sort of, it does matter, but I'm just taking it in an instant in time. Yeah.
Is the spread like quarter one of the central frequency
or? Smaller. No, it doesn't have to be 1,000, but smaller. Yeah.
Okay, so like
this is just saying that you have a, am I right? I'm just saying that you have a curve with some pitch, right? So you have a spectrum. Something like this. It's not super broad.
Yeah, so if I like, if I tried to draw the electric field off of this, like I put little wiggles on inside this envelope, but there would be like many wiggles.
Exactly, yeah.
Okay.
Exactly, yeah.
Maybe we expand it, but again, so does the size of the fluctuation depends on the overall intensity, like average intensity of this source?
This fluctuation? I mean, yeah, you have some mean intensity, and then the
Imagine the situation where the average intensity is kind of higher and higher. I mean, what happens to the size of the fluctuation? Is it the same? Relatively the same or just
well, the fluctuation over the average remains constant.
Okay, so it doesn't depend on the.
No. Yeah. So it's like I don't know, putting like having an electric field and having, E1 plus E2 with a dephasing, which gives you, 1 plus 1 compared to E1 plus E2 in the same phase, which gives you instead of 2, 4.
Okay.
Yeah.
And the size of the E1 and
Yeah, exactly. Yeah. All right. So if you had two telescopes, two photodetectors, and that's where interferometry comes in. If you had two photodetectors, say they are perfect, they can measure this wave passing through with perfect precision in time. Both of them would see an upshot in fluctuations if they were, close together, either in space or in time, right? So if I have two photodetectors here, and then in the center of them I have a source, right? They see the same. They see the same wave coming into them. So they would both see a positive fluctuation in intensity. They would both measure this. Whereas if my telescope was farther away, there is no correlation. This is some random macroscopic fluctuation. This is some other random macroscopic fluctuation. So if you think of this as N1 times N2, number of photons here times number of photons there fluctuation, you would only find short noise. So this is telling you again, similarly to the Michelson interferometry, where as you're taking your telescopes farther away, you lose the interference. Here, as you're taking your photodetectors farther away, you're losing this positive fluctuation, positive macroscopic fluctuation correlation of the two telescopes. So this is how you can infer distances, for example. Okay. Now, a detail here, which is pretty important, is the fact that your photodetectors are not perfect. So actually, you never see this full thing. You never see the full fluctuations here, but you see your telescope is sort of smeared out in time. So you get a suppression by the fact that you cannot pin it down to a femtosecond. Basically, the best photodetectors can do today is picosecond, maybe a few picoseconds. Back then, when the technique was proposed, it was nanoseconds, 10 nanoseconds. But the suppression that you get is linear. It goes like the coherence time of light, which is 1 over the bandwidth, over the resolution of your photodetector sigma t. Okay? All right. Any questions before I go to stellar diameters? Okay. So the observable of intensity interferometry is quite similar to the one of regular Michelson interferometry. There it was the visibility. Now it's the modulus of the visibility squared. This is something you can prove. It is the correlation instead of electric fields of intensity. So you get a 4-point correlation function of electric fields instead of a 2-point correlation function. And you can prove, similar to this van Zitter-Zernike theorem, that here you measure the Fourier transform of whatever intensity distribution you have on the sky, but actually it's modulus squared. So what you lose with intensity interferometry is phase information. Before you measure the complex number, an amplitude and a phase, but here you are only measuring an amplitude, or the sum of real part plus imaginary part squared. And this image here is just actually a diffraction limited image of Sirius, which is the first star that was measured using this technique, the diameter of which was measured using this technique. And the basic problem of intensity interferometry is because it's a 4-point correlation function of electric fields, you need more photons to pin down this observable. And the SNR scales like the number of photons compared to the square root of number of photons. Now you would say, wait a minute, it scales like a larger power, so I have many photons, this would be larger. But think of this as the SNR over an observing window, over a sigma t window. This is the SNR that you get, and then you improve by the square root of observing time, by the square root of observing time. But over sigma t, over the resolution of your photodetector, even whether it is 10 nanoseconds, which is what they did back then, or picoseconds, which is today what we can do today, this is a number smaller than 1. Okay, basically, if you look at the star that has a magnitude of 3 or more, like regular stars on the sky, the photon, you get 1 photon every microsecond, or maybe half a microsecond, not every nanosecond. Okay, basically, if you're using a photodetector, whatever photodetector you use, you measure all the photons that come from the star on Earth. Right, so this is why I'm saying that this is a much harder thing to observe, because this case like n photon which is smaller than 1. Okay, and the other thing is that you don't get phase information because you measure the modulus of this quantity. So if you had a star with a sunspot, you wouldn't know where the sunspot is because this needs phase information to pin down exactly on the image. However, you can measure things that have real visibilities, and there are many celestial objects that do that. Actually, any function that is cylindrically symmetric has a real Fourier transform. So even if you have a complicated source and you break it down to spherical harmonics, you would be able to measure all the spherically symmetric ones. Sorry, azimuthally symmetric ones. And case in point, if you have a stellar disk with uniform illumination, and you calculate the Fourier transform of this, you find the real function. It's this Bessel of x over x. And here I'm plotting visibility squared. So as before, as I'm making my baseline larger, I start from 1, and then I'm losing the correlation as I'm taking the telescopes farther and farther away. And then I know, when I don't measure this correlation anymore, I know that I resolved my source. And this is what I did to measure Sirius for the first time. All right. Here is an image of this observatory in Australia, the Narrabri Observatory. And I want to drive home the fact that this is a cheap thing to do. This was done in the 1970s. This is before adaptive optics. So I'm talking about extremely good resolution before being able to do anything about the atmosphere, okay? So they had these two mirrors on tracks, and they moved the mirrors, the telescopes, with their hands, okay, on these tracks. And the only connection are these cables, which just, give the transfer the photon counts to some central facility. There's no interference of light, physical interference of light here. And these telescopes were stored in this place here, okay? So this is super rudimentary. And the way they assemble these mirrors, these are 6-meter mirrors, right? These are huge for standards back then. The way they assemble them is they took these roughly parabolic pieces that knew roughly what is the focal length and just assembled the mirrors by hand. And you would say, well, this has terrible optics, and that's true, it has terrible optics, but you don't care, because if your resolution is 10 nanoseconds, this is 30 centimeters. 30 centimeters in path length, making this precisely within 30 centimeters is something trivial to do, okay? So in this sense, intensity interferometry is cheap. All you need is to observe as many photons as you can. And this is what they did. They measured all the stars in the 1970s. And as you can see, all the stars have names. And the reason they have names is because they are the brightest on the sky, which is this SNR problem I was telling you. You need really bright sources to do this. And in a sort of an unfair comparison with the resolution of M87 here, the precision that I got in some stellar radii is the same as what EHT was able to do with baselines as long as the Earth. Clearly, this is unfair. This is radio, this is optical, this is not even observable. I mean, this is, yeah. But you can see a sense of the resolution, what objects we could look at if we had a big enough SNR using these baselines, okay? All right, the limitations, as I told you, is the SNR. You need very bright sources. Also from and the main reason is this suppression I was telling you, because your photodetectors are not perfect. You get a suppression from the coherence time of light over your photodetector resolution. So back then, they used PMTs, which are 10 nanoseconds. This number I've been quoting all this time. And the coherence of starlight, it's optical, so it's femtosecond. Now, clearly, this is a huge suppression. It's 10 to the 6, 10 to the 5, 10 to the 6, which makes this completely hopeless. But what you can do is artificially change the coherence time of the light source you're observing. And the way to do this is with a filter. And that's what they did. They used the narrowband filter in front of their photodetector, and were able to make this quantity larger. However, today we can gain a lot from new technologies. And this is why all the applications that I'm going to talk about are possible today and were not possible even 10 years ago. So first, we have very fast photodetection. We have new devices which are called SNSPDs or SPADs. These stand for superconducting single photon diodes. And this is how this whole thing started from particle physicists, because there are dark matter experiments that use superconducting devices. And what happens is you have a pixel, you have a cable that is superconducting, a photon hits, breaks superconductivity, and you measure the pulse. You measure the voltage from the resistance that it makes. Or you have diodes, SPADs, single photon diodes, where you have a diode, you have a reverse current, and when a single photon hits, it creates an avalanche, so you can measure single photons. And the time resolution of these devices, the spread of these pulses, can be 10 picoseconds. Actually, there have been ones demonstrated even with 3 picoseconds. So this is already a factor of 1,000 better than what they could do back then. And the other thing that we can do now that they couldn't do then is spectroscopy. It's a much more mature technology today. And so instead of using filters to artificially change the bandwidth of your light and throwing away all the photons that are not in your filter, you can create many effective filters by just dispersing light and having one photodetector for each bandwidth. And we can do thousands of these things with off-the-shelf instruments nowadays. All right, so this is how we can go from magnitude 3, which is what the stars they were looking at are, to magnitude 11, which opens up the possibility to look at AGNs. Okay, very fast introduction to AGNs. What we think they are is supermassive black holes in the center of galaxies with an accretion disk that is emitting, has very violent processes happening and emits a lot of light. In terms of magnitude, this can be as bright as magnitude 11, if that tells you something. But the angular scales of these AGNs are very small. So if you're looking at something like the ISCO, this is below a microarcsecond. So if you wanted to do optical interferometry, you would need a baseline from 400 to 4,000 kilometers to observe it. The range is, I took some AGN at 400 megaparsecs, which is actually pretty close. And this range comes from, maximally spinning black hole. And this is an artist impression. Yeah. Yeah, you cannot hope to resolve an AGN with any other means that we have today. And even the mean radius, you have some profile and some mean emitting radius. Even this is on the order, you would need a baseline the order of 20 kilometers. So it is hopeless to do optical interferometry to resolve these AGNs.
But sometimes people see the jets because they go far away.
Yeah, if the jets are far away. But the accretion disks themselves, you cannot hope to resolve. However, these are all baselines that fit within the Earth. So you can do something with intensity interferometry. And sure, you cannot take an image of an AGN disk like the Event Horizon Telescope did. But what you can do is measure some parts of the intensity distribution. So for example, if you have, this is just a toy example, a Sakura Tsunaive disk, which is symmetric. It's cylindrically symmetric. The temperature profile is given by this, and then you just calculate the Fourier transform as we did before, and you see the features. You see the mean intensity, which starts decreasing your correlation, and at some later point, you see these sharp oscillations that come from a sharp P-score. And actually, if you run the numbers, and you have something like the CTA array, which is the HREConf telescope array that wants to look at gamma rays or X-rays from AGNs, actually. And they are just big mirrors that are not perfect, have big aberrations, but they're just big enough because all they care about is collecting a ton of X-rays or gamma rays. And they already do intensity interferometry. It's just that they use PMTs. And I can tell you why they cannot do what I'm proposing. You would need a CTA array that is different than this, but this is, again, a cheap thing to do. These are cheap telescopes. So with the CTA array, photodetectors that exist today, spectroscopy that you can just go and buy a spectrograph that does this. In 24 hours of observation, you get an SNR of 2000. And if this doesn't tell you much, it tells you that in something naive like this, you can measure the ISCO to 6 sigma. Clearly, this is not the right picture. This is, you would need some GR MHD simulation and fit your data to that. But the point is that we would be sensitive to flux from near the black hole. Okay, and this is impossible to do with anything else, any technology that we have. Okay, right. And actually, you can use these AGNs to do something to do cosmology and measure the Hubble constant. And this will be by combining intensity interferometry, that I just told you, and reverberation mapping. Okay, so what reverberation mapping is, again, I'm going to give you a 1-minute introduction. We have this black hole, this AGN, and the accretion disk around it. And what it does is it emits light. So think that you are an observer somewhere here. And what you see as this thing fluctuates, you see a train of a luminosity as a function of time that comes from the blue, the photons that go through the blue direction, which has some fluctuations. But then this, as it's emitting photons, this thing grows radially, and it hits gas in the outskirts of this AGN, in this dark black region here. And it excites this gas, and this gas emits. But it emits on a line. It's line emission. And what you see is basically this continuum, this random thing that is happening in the center of the black hole. And at some time later, you see the exact same fluctuations imprinted on a line emission. So you see, this on all wavelengths, and then you see this on the H beta line. Okay, and this is called the broad line emission region because, okay, this is complicated physics, but in a very naive way, you can think of this as an accretion disk. As a Keplerian disk, very far away. This is like 10 to the 5 GM in these units. With Keplerian velocities. And for a supermassive black hole, 10 to the 5 GM gives you something like 10 to the minus 2 of C of velocity. So you see some Doppler broadening of the line. And that's why it's called broad line. So by seeing these fluctuations in the continuum, in this blue and in the red, by measuring the time lag, you can know what is the path length here, the time it took for the light to go from here to here in physical units, in centimeters. So by taking a picture of this thing with intensity interferometry, you can know the angular scale. And by doing reverberation mapping, which already surveys like SDSS do, you can measure the actual size, and you can solve for the distance. And by doing this, this is sort of preliminary, but by doing this, you can, with the brightest existing broad line emitting AGNs and the parameters that I told you before, which are totally realistic, you can measure Hubble to within, 3%. start resolving the cosmological tension.
Can you go back?
Yeah.
Yeah, what's the characteristic with the animations? So basically, I'm trying to observe the light intensity, right? So I record it as a function of time and see later on that feature appears again. So by say, oh, this repeats the pattern, so it must be some edge reflecting the same source.
Yeah, which is why it's called reverberation.
Does it require so in my device, I still just count photons in this big block. I just check what's the reappearance time of the pattern of the design.
Yeah. Essentially, I mean, there are degrees of complication because you can do spectroscopy also, and that gives you more information. But the simplest thing you can do, the simplest thing you can think about is having some intensity as a function of time for the continuum, for the blue one, and you see something like this. Okay, and when you observe at some time later, and this time scale is of order of days, weeks, depends on the AGN, because it's far away, it's 10 to the 5 GM. This is on the order of days or weeks, depending on the mass of the black hole. And then the broad line would look something like this thing shifted, so it would be this. Right? Well, this is shifted. Yeah, something like this. And by measuring this time lag, this thing, you can know in physical units what is the size of this. It is more complicated, but this is the secret.
But I would assume everybody's doing this observation. You're saying nobody's doing this.
No, reverberation mapping, they are. Yeah. What people haven't done is combining this with intensity interferometry to do Hubble.
I see.
But this time, like, yeah, people do them, and by doing this and by doing also spectroscopy to learn something about the velocities, you can measure the mass of the black hole. Yeah, and people measure masses of supermassive black holes in this way.
So reverberation is the intensity measurement, but it didn't do intensity interferometry. That's what you proposed.
Yeah, these are different telescopes that do this. Reverberation you would do with some other array like SDSS or whatever, some survey, and intensity interferometry you could do with other bigger telescopes.
For the intensity interferometry side, like you basically just need to figure out the angular distance between the black hole and this cloud, right?
What you need is this size. Not the black hole, but this. What you measure is this size, right? If this is a circle, you measure the diameter of this.
Which you said is like 10 to the 5
Yeah.
EM. So that's actually not that small of a scale, and like you don't need to do so well that you can resolve the ISO.
Right. Yeah. These are two different applications. Yeah, you're exactly right.
Much
Yeah. Exactly. So this you can do tomorrow. Yeah. If you had just big, large piece of glass.
So what your interferometry does is just place the black hole in the exact position so you can get that.
Well, it measures the angle. I don't want to say it places the black hole, but yeah, assuming that whatever you have some model in the end, and then you feed your data to the model. But yeah, if you have something that is azimuthally symmetric and it's a circle, yeah, it pinpoints the black hole in the center of the circle. Yeah.
Also, how fuzzy is this cloud? Like, it's not some one particular range.
Yeah, it can be fuzzy. Yeah, you can do all sorts of things after. I mean, this is the simplest thing you can do, but usually, yeah, it's like a black hole, and then you have the PLR can be from 10 to the 3 to 10 to the 5. So in the end, you have some model on what this looks like, and then you feed your data to the model. But in principle, yeah, it's not a thin thing. It can be quite extended.
But you need to do some modeling.
Yeah, like rolling the front, PhD. And
sorry, can I jump in from outside? I have a question. Hi, it's Roger Rusak here. Yeah, I have the question. So just to understand what you're saying, you're looking at this particular source. You see the initial fluctuation from the black hole itself, and then we see later the fluctuation as it hits the ring around it. That's the basic concept. Are you trying to see? You're looking for the fluctuation, so you're trying to find the same mapping of fluctuations in two different wavelengths and two different times. So you're talking about separation of the events, which could be weeks. are you sampling at the rate? So are you still sampling down in the picosecond range, or is this much larger fluctuations that you're looking longer fluctuations?
Yeah, that's a good question. Yeah, to clear any confusions, this is just traditional reverberation mapping, which just looks at the particular AGN every few days. This is not picosecond sampling. You don't need super fast photo detection to do this.
So
Well,
you look at the time variation of the signal
Yeah.
in one wavelength, and you compare it and some interval later with what you're seeing in another figure, and you're looking for the same pattern of fluctuations in both. Is that that's
Exactly.
right? You're looking for the time separation. Okay, that's pretty clear. Okay,
Yeah. That's traditional reverberation mapping. All I'm saying is that you can take the data from this, add to them intensity interferometry, and then you get Hubble. But intensity interferometry is completely different from this
Okay.
one.
Okay. I'd like to talk to. We'll ask questions about the other one, which I think. But please go on. I'll have questions at the end.
Okay, sounds good. Thanks. All right. Well, I'm out of time, so I don't really have time to talk about this. Okay, what should I do?
I mean, we start a little bit
Well,
more.
it's like I have 5 minutes.
Yeah, if you don't think you can do it.
Yeah. Okay, so in 5 minutes, the super fast introduction of this is what you're trying, right? So what we want to do now is relative astrometry. Before we were trying to measure sizes. Now what we want to measure is the distance between the two objects, which are two stars. And the problem that arises, I just tell you what the problem is. So if you have two things that are separated far away, basically you have 4 path lengths, okay? And as I told you before, when the path lengths become vastly different, your correlation is washed out. So there's no hope of seeing two stars that are, let's say, an arcsecond apart if your baseline is a kilometer. A kilometer would have a resolution of a microarcsecond, so it would over-resolve these path lengths, and you would get 0. So the problem, what you want to do to measure things that are far away is make all these path lengths the same. Okay. The first thing you can do, which is what all radio telescopes do, is change your clock. So if you shift your local clock, you can make 2 of these path lengths the same. And I chose it here in such a way that the path lengths from star A are the same for telescope 1 and telescope 2. But because the two sources are always far away, if I change my local clock, I change both of them. So with a change of the clock, there's no way to do astrometry, to measure the distance to be more precise, I want to have a distance that is x and a precision of the distance that is x over a large number, over 1,000, over 10 to the 6, right? Arcsecond with microarcsecond. So there's no hope to do this with just a shift of the clock. And this is where this extended intensity correlation comes in, is to try to do in hardware this extra path length difference. And what you would need to do naively is change just this blue path length, make it a bit longer. And I just add this here pictorially. And what happens is I put one star on top of the other, and the path lengths are the same. So this is the idea. You would like to change only the path length from one star with some hardware modification. Okay, I'll just skip this. The way you do this is by putting some module in your telescope. So you have light coming from 2 stars. It comes in your primary mirror, it gets recollimated, and then the light from both stars goes through this module, this extended path intensity correlation, or EPIC for short module, where it gets split by a beam splitter. So now you get star A and star B going up, and star A and star B going down. There are four, in the end, when you recombine, there are 4 pairs, right? There is star A and star B going in the lower path, which has no differential path length difference between the two, so that's useless. The same thing on the upper path is also useless. Also, the wrong correction is useless, where star A gets more a longer path length compared to star B, but there is one useful one. One of the 4 is useful, and it's this one. It's when the star B goes this way and star A goes the other way. You get all 4 in the end, but only one of them is useful. And what happens is, if the Fourier transform of 2 stars is a cosine, So this is what you're seeing here. It's the cosine and the decay of the correlation at some large angle. And this angle is less than an arcsecond, much less than an arcsecond. This is like 0.1 arcseconds. And by doing this extended path intensity correlation, you get this spike in a log-log plot. What you actually get is this. So you have some reference angle, you have your arcsecond, which is the separation of the two stars, but you can measure it extremely precisely with a microarcsecond light-centroiding precision. Well, resolution, and then even better light-centroiding. Okay, that's the idea. I'll just show you this last thing. For a pair of blue giants that are, some reasonable distance away, I forget what this is, I think like maybe a kiloparsec. In a single night of observation, 3 hours of observation, you can gain a precision, a light-centroiding precision that is 0.1 microarcseconds. And compare this to the best Gaia can do, which is 10 microarcseconds after 30 years, okay? Clearly, this is different. This is a single pair of stars. It's not billions of stars. So but the applications of this are different from Gaia's applications. So now I can do extremely precise astrometry. And I don't have time to explain the scientific applications. I'll just say that we can probably measure the length steering precision of the stars in the center of the Milky Way with this extreme precision, and you can ask me more if you're interested. So I'll just conclude. Yeah, and someone is trying to build this at Carnegie, build a prototype. Nick Cornetiers, yeah. All right, I'll leave the conclusions here, and I'll take any questions. Thanks. Yeah, so, right. So there is a protocol on how you would do this. The idea is the following. So Gaia will have, these are bright stars. These are still stars that are brighter than 15, basically. So Gaia will have a complete catalog by the time, like this is here. So in principle, you take some theta initial, right? Some separation that comes from Gaia. That is going to be something like, I don't know, like let's say an arcsecond. By the way, you can ask me where the upper limit comes from, the atmosphere. Plus or minus, let's say 10 microarcseconds. Okay. Then if I have a baseline, my baseline D is such that, lambda over D, the baseline I choose is 10 microarcseconds, roughly. Then I can be in my central fringe. I know it well enough to be on the first fringe of the cosine, right? I have this cosine I showed you of the two stars, and I can be within this, with this error. If I don't have Gaia data, because as I told you, Gaia cannot see things that are closer together, what I can do is do a logarithmic iteration in baselines. So if I have an array of these telescopes, which are again cheap and you can do that, you would start with a resolution that is, let's say, like 10 milliarcseconds. And then you make 10 milliarcseconds, and then you measure this sigma theta, you measure it with lambda over D, but you light-centroid better than lambda over D. So you just get an SNR of, let's say, 10, and then you can go to 10 times longer baseline. So with only logarithmic, basically 2 or 3 baselines, you can reach the maximum baseline that is allowed for this stuff.
So I guess there are 2 questions. One was that application where it's very, this I should say you would, I guess in this case, look at 2 stars very carefully and do things on the structure. And second is that, do you have numbers for each dot from the previous stuff we talked about?
You mean how well you can do in each node? Yeah, sorry, yeah, I went quickly through this slide. So these lines here are, this is the flux of some particular AGN, and the lines are, okay, the lines fluctuate in general, but this is, I took it from some plots of these AGNs, and these are known AGNs. So by doing that, by just looking at those AGNs with these parameters that I'll do in 24 hours, you can gain anything from 3% Hubble to 1%. Yeah, well, this hasn't been built yet, but this is what I'm advocating for it to be built, because you can do this very easily.
You'll use the char array to do this?
Right, so you would need baselines that are long. You would need to build an array from the beginning. You would need baselines as big as 10 kilometers. And even the CTA array is at most 1 kilometer. So you need to build something different. But again, it's cheap. You can do it.
I'm
It's
sorry.
cheap for astronomy, right? Astronomy, like a few million, tens of millions of dollars is nothing for astronomy.
Would you need to align every detector to the picosecond level within if you're doing that?
No, you need to align them to within the oh yeah, picosecond. Yeah, this is millimeter. Yeah, that's right. Yeah.
So you need to align the detectors across. You said I didn't quite hear your answer. Was it 10 kilometers?
Yeah, you need to know the baseline, the 10-kilometer baseline to within a few millimeters. Yeah.
And the clocks need to be aligned to within picosecond.
Exactly. Yes. So you need, right. Yeah, but this is what the HT is doing, right? Their wavelength is millimeter, so they're both doing baselines and clock synchronization to this resolution.
Over 24 hours?
Well, yeah. Right. So what you would do in the end, like when you do the observation, is split it into smaller chunks.
Yeah.
And then synchronize your clocks in these smaller chunks, and you can do that because your SNR is more than one, basically every minute. So
Yeah.
that's something doable. Yeah.
And your sampling rate is the picosecond. So you're sampling at gigahertz. Is that right? So you're counting the photons in a particular detector in an interval, the number of photons you get in the interval of like 5 picoseconds.
Yeah, I get photon counts every picosecond. Yeah.
Right. So you have to, so this is with your spats. And then you will go, and this is all the way across the array. Okay.
Yeah, I'm sampling every picosecond, but I'm not getting a photon every picosecond.
No, I understand that. But you've got to have your alignment of your clocks and the sampling all in phase.
Yeah.
At the picosecond level, right? Okay.
Yeah. So synchronizing your clocks to picoseconds, you need some atomic clock reference in every site. But that you can do with cheap atomic clocks in the sense that you don't need a hydrogen maser. You can do it with rubidium or cesium clocks because your SNR is big enough. If you had the source that you would need 24 hours to do it, it would be hopeless because there's no synchronization that can work for 24 hours. But over a few minutes, resetting every few minutes is totally doable. Yeah.
Okay. I mean, I ask because actually this is a problem we have in CMS. I'm a high energy physicist, probably like you, right? And we're worrying about how to distribute clocks that are stable over large areas. Okay. So it's a picosecond level. Okay.
Yeah. Any other questions?
Yeah, any final questions, Marios? If not, let's thank him.